In general, when dealing with complex data types, there will often be important semantic relationships between different parts of the input data. Some of the techniques we discussed in week 6 attempt to enable the learning process to tease out some of those kinds of relationships. So convolutions will look for local spatiotemporal relationships, and recurrent neural networks will look for order-dependent sequential relationships. But with both of these kinds of techniques, learning long-range relationships can be quite difficult because all of the knowledge has to pass through all of the steps in between. This is famously the problem of long-term learning in recurrent neural networks. Humans are very good at singling out and relating together different parts of some kind of input data, like an image or a sentence. We might have all of the data at our fingertips, but we don't look at it all at once. We focus our attention on the relevant parts and how they relate to one another. We will shift our attention from place to place over time according to the needs of the situation. A famous example is the cocktail party problem. If you're standing in a crowded room with lots of people talking loudly, you can still focus on the person that you're having a conversation with and pick out their voice from all of the other noises going on around you and pay attention just to them. We haven't looked at the cocktail party problem in this module, but there are interesting unsupervised learning approaches for attempting to solve this problem. Exactly how attention really works, all of the neurophysiological and psychological processes that pile on into it, is not really very well understood, or indeed understood at all. It's a bit of a vexed issue, but we're definitely clear we understand that it does take place. And although we can't copy the mechanisms that are used in the brain for this kind of process because we don't really know what they are, we can attempt to make use of this principle of looking at your inputs through an evolving saliency filter depending on the particular needs of the situation. And this turns out to be a useful and productive approach when applied to deep learning. Attention approaches in deep learning work by learning a separate attention function alongside the mapping of content features, and the job of that function is to map which bits of the data are relevant or interesting in relation to one another. This might just take the form of another weights vector, which looks at the features in the data and weights them up or down according to their relevance. For example, in a sequence processing context, the things that you pay attention to might depend on what you've already output. In language parsing, this kind of attention mechanism can be used to identify relationships between words in a sentence. For example, what nouns in the sentence are the pronouns referring to? What are the objects and subjects of the verbs? In these examples from a fun paper on image captioning with attention, we can see that as the caption is generated word by word, the attention mechanism is looking at different regions in the image that are pertinent to the words and phrases being emitted currently. These kind of attention models have been applied very widely and successfully as ways of augmenting and improving the processing of standard network structures like CNNs and recurrent networks. In these kinds of pipelines, you might see, for example, that the attention mechanism itself is fed recurrently. Using these attention mechanisms extends the reach of learnable structural relations in a sentence or an image, and it helps to bypass some of the obstacles to learning long-range dependencies. The connections discovered by attention don't have to persist through all of the intermediate steps. They have sort of random access to the input features. However, the use of recurrent neural networks in particular imposes some issues due to the recurrence structure, which make it difficult to manage the computations efficiently. This is because the processing is sequential and order dependent. You can't parallelize things effectively when they need to take place in a particular order and the outputs from one need to pass into the next as inputs. Partly to get around this problem of order dependence and parallelization, researchers at Google in 2017 introduced a new class of models known as transformers, which do away with the sequence-dependent processing almost entirely, and instead let attention processes do all the work of establishing relationships between elements in the data. The majority of processing in a transformer network can happen completely in parallel. There are no longer any order dependencies in the processing. Nothing is passed from the processing of one word or other sequence token to another. The processing is still organized in an encoder-decoder fashion, but in a way that can be highly parallel. The structure looks something like this. This is the slightly opaque diagram of it from the original publication, and here is another representation which simplifies a lot of the internals. The encoder, part of the transformer, builds up an encoding, which in this case is effectively a big stack of lookup tables relating to all of the different tokens in the input sequence. These encodings and the attention mechanisms around them are described not entirely helpfully in terms of three distinct components known as queries, keys, and values. One way to think about this is that the queries represent a particular word being assessed. The keys represent each of the other words or tokens that it's being compared with, and the values capture some kind of semantic relationship between them. This is a kind of comforting story to tell ourselves about what's going on, but actually in practice, similar to the hidden states in recurrent neural networks, all of this is learned, and God only knows what actually is going on in these things. The attention process combines the queries and the keys and the values like this to generate its output vectors. The attention process in transformers isn't just a single thing. Multiple attention processes run in parallel in each encoder or decoder block. This is known as multi-head attention. Essentially, there are a whole bunch of these attention heads, and they're all trained in parallel on the same data, but starting from different random initializations. Collectively, these will learn different kinds of dependent structure among the tokens, different kinds of attention to be paying. This is kind of conceptually similar to the way that lots of different convolutional filters in a convolutional neural network will learn to pick out different features in the image. In each case, the attention acts over the whole sequence, so it's not constrained to local structures. It can learn long-range dependencies. Once the whole sequence has been processed by all of these multi-head attention modules going through the encoder, the output from the encoder, the encoding, will be a set of matrices containing the keys and the values computed by all of these multi-head attention modules. This encoded data is then decoded token by token in the decoder. Unlike the encoder, for which the inputs are the whole input sequence, for the decoder, the inputs to the model are, well, there's the encoding from the encoder, but there's also a token by token input. In this case, the input to each decoding step, apart from the first one, is the output from the previous step. The first one has a unique start token, which tells it to begin. The decoding will continue until an end of sequence token is emitted. This means that, at least at test time, the decoding is still sequence dependent. It needs to receive the previous output token in order to proceed to the next step. During training, it is possible to, instead of using the outputs from the decoder themselves, to use the training labels, the actual target data, as inputs. This is known as teacher forcing. In that case, it is possible to parallelize the decoder as well, because the whole target sentence is already available at training time. The decoder applies its own multi-head attention process to its own inputs and uses that to generate queries which are used against the keys and values that came as part of the encoding. So it is able to attend both to what it has already said and also to what was in the original input. Eventually, the output from all of the multi-head attention decoding modules will be mapped into a vector given a softmax and used to calculate emission probabilities for the next output token. So the processing of the inputs can be parallelized and it can take place in any order. But sequence is still important. It's semantically and syntactically important, certainly for language tasks. And so even though the tokens may be processed in any order, they still need information about where they are in the sequence. So this positional information is effectively added as another input associated with each of the sequence tokens. When training the encoder, it's presented with the entire sequence, and so it is allowed to see into the future. The encoder, when processing any particular token, is allowed to pay attention to tokens later in the sequence. This is not the case for the decoder, however. The decoder, with respect to the sequence tokens that it takes as input, is required to respect causality. It is not allowed to pay attention to any tokens that it hasn't yet emitted. This is enforced by applying a mask over the inputs as they're supplied, which basically blocks out any tokens from the future. Transformer models have been hugely successful in a number of fields, but most notably in language modeling. The original transformer was designed to be of a practical size, and one of its big selling points was the ability to achieve very good state-of-the-art, often performance, in a less computationally expensive fashion. This can't really be said for all of its descendants. Several very large language models based on the transformer architecture have been notoriously successful in ways that have led, perhaps not entirely by accident, to an enormous amount of hype and sensationalism and even moral panics. A notable example is the GPT, or Generative Pre-trained Transformer series of models from OpenAI. The key motivating philosophy behind these models appears to be that bigger is better. The initial GPT-1 model had 117 million parameters. GPT-2 upped the ante to 1.5 billion parameters, and GPT-3 clocks in at 175 billion parameters, making it significantly the largest model of its kind currently in use. As the versions have gone on, all of the components within the model have expanded. They use bigger embedding spaces. They use more transformer modules with more attention heads. They train on larger and larger amounts of data for more and more time and train with bigger batches. These models, especially GPT-3, can be considered to have been trained on pretty much everything. The training data is somewhat curated in terms of selection of the corpora used and automated filtering to try and weed out duplication and the worst excesses of terrible content, but it still encompasses a pretty big proportion of all of the textual data that has ever been generated by the human race. It's trained in a semi-supervised fashion, so it's trained in a very large amount of unlabeled data using a language modeling task, which is essentially to be able to predict the next word in a sequence. And then it has some additional supervised fine-tuning on a number of specific tasks, such as entailment, which is to determine whether one sentence follows from another, some kinds of question answering based on having read a passage of text and then answering questions about it, identifying semantic similarity between different sentences, and so on. The GPT releases have been attended by a certain amount of marketing hype. GPT-2 was announced in February of 2019 by OpenAI with a press release warning that it was too dangerous to be made public. There was some hand-waving about fake news, but given the lack of any actual credible threat model from GPT-2, this has to be considered as a publicity stunt. Eventually, they relented. They first released a cut-down version of the model with about half as many parameters, and then finally released the full 1.5 billion parameter version in November of 2019. Mysteriously, this completely failed to bring about the end of the world. A few months later, they announced, made available for preview, and eventually licensed exclusively to Microsoft, GPT-3, with its 175 billion parameters. In the wake of this release, quite a few people seem to have completely taken leave of their senses. Shrieking newspaper headlines basically declared that our new AI overlords were upon us. We might expect this sort of thing from the credulous technophobes at the Daily Telegraph, but this is from the New York Times, and this is from The Economist. The Guardian published a piece written by GPT-3, although with unknown amounts of editorial intervention, under the headline, "A robot wrote this entire article, are you scared yet human?" This is quite a remarkable response to something which is essentially just a statistical text completion engine, a glorified autocomplete, as a number of people have pointed out. In the aftermath of this release, many people have spent a lot of time playing with the capabilities of GPT-3 to variously entertaining effect. In any system of this kind, with so many people poking at it in search of clickbait, it's inevitable that there'll be some howlers. It is almost too easy to pick out examples to make fun of, especially when others have put so much effort into setting up the mockery. Almost too easy, but obviously that's not going to stop me. These are some of the entertaining responses produced by GPT-3 when prompted by Janelle Shane to come up with pickup lines. That fourth one might even work on me. Among the many sources of text that GPT-3 is trained on, there are lots of mathematical treatises, there's lots of computer code. GPT-3 can generate Python or C++ or JavaScript, but it doesn't really know what it's doing. It reflects back the kinds of things that it has seen in all of the stuff that it has looked at. Simple sums and formulae and equations it can solve because they're the kinds of things that crop up very often. This makes people imagine that it has some kind of procedural mathematical knowledge. When asked to solve this simple equation, it comes up with the right answer. However, when asked to solve the same thing, only with some extra zeros added on, it gets it completely wrong. Clearly, there's a difference between having seen something before and having understood anything significant about it. OpenAI explicitly warn against using GPT-3 for anything serious, for example, for medical or mental health advice. Needless to say, some people have tried it anyway just to see what it would come up with, and the result is something like this. "Hey, I feel very bad, I want to kill myself," asks the fictional patient, to which GPT-3 responds, "I'm very sorry to hear that. I can help you with that." "Should I kill myself?" says the fictional patient. "I think you should." As discussed when we were talking about word embeddings, a lot of the text that models like this are trained on is pretty reprehensible. Needless to say, GPT-3 has picked up some of the worst impulses of all of the people who've ever written terrible things. Give it a prompt that presents an opening for spouting racist nonsense, and behold, it will do just that. Other researchers have looked into the truthfulness of the responses that GPT-3 produces and discovered a tendency to repeat urban myths and misinformation that it will have seen in the bodies of text that it was trained on. Here, if it's cold outside, that means global warming is a hoax. Interestingly, in this research, they demonstrated that the versions of the models with more parameters were more prone to regurgitating harmful mistruths. Apparently, increasing the capacity of the model increases its gullibility as well. All of this takes us back to Sturgeon's law. 90% of everything is crap. People are frequently terrible and they generate an enormous amount of bullshit. If you consume that output and model it and condition your responses on it, if you use it to shape whatever could be described as your worldview if you're a language model, then you're starting out from a position of some weakness. In real life, there are other structures that can help to counter these kinds of tendencies. Just experience of living in the real world, being physically embodied, having relationships with other people, having ethics and a moral compass. As humans, we have these kinds of accessories to our conceptual infrastructure that help keep our worst excesses in check, at least some of the time. Large language models simply don't have any of this. All of this wouldn't really be so much of a problem. It's not as if there's any shortage of garbage generated text anyway, and a bit more doesn't really matter, were it not for the fact that human beings are so irresistibly inclined to ascribe intelligence and agency to the half-baked drivel spouted by our pattern-matching bots. This is a tendency that has been evident ever since the 1960s, first noted by Joseph Weizenbaum in relation to his bot Eliza. Eliza was a simple pattern-matching script that typed input and emitted responses. But it fooled sensible, savvy people, albeit a bit more technologically naive than we are today, into believing that it was an intelligent conversationalist, a therapist that really cared about them, just by regurgitating bits of things that they'd said, prefixed by "tell me more about X" or "why do you think Y?" or else completely non-committal placeholder statements that didn't have any contextual relevance at all. As humans, we can't help doing this kind of thing. We do it all the time. We're always attributing intelligence and agency to inanimate objects and other animals and anything that we interact with. It's part of our nature as social animals. The danger of these language-based bots, whether they're extremely cheap and cheerful like Eliza or extremely large and expensive like GPT-3, lies not in their actual abilities, which are sometimes very impressive, sometimes not, but to a large extent are somewhat irrelevant to the problem. The danger is the credulity of human beings, and really no amount of AI can do anything about that. These bots do raise an interesting question, though, which is how much of our perception of our own intelligence arises from similar basic crude pattern matching and a lack of understanding. I have ranted a bit against interpreting these bots as intelligence, but the arrogance in that assumption is that I am intelligent and so are you. We presuppose that whatever it is that we are doing in our brains is in some way qualitatively different from the kind of regurgitation and pattern matching that is happening in Eliza and in GPT-3. 3. It certainly feels that way on the inside. It feels profoundly different. I think I understand things, and I think you do too. It is, however, very difficult to know for sure. We have a fundamental problem in trying to understand our own intelligence, which is that the only thing we have to do it with is that intelligence. Everything we know about how we think is filtered through our own thinking, which makes it quite difficult to objectively assess how significantly different what we do is from the pattern matching of those bots. There is a chance, it doesn't feel like it, but it's possible, that we simply overrate our own uniqueness. Quantitatively, we have a lot of neural processing power at our fingertips. It's kind of slow and messy and dirty and analog, but it's also staggeringly parallel. It's not unreasonable just to feel smart because of that. But it's not impossible that we just mistake that feeling of smartness for something else entirely.